let's continue the function f. So f depends on z. So, but likewise, any function which is most likely a complex function, also because z is already complex, and whatever expression will like to make f a complex function also. So f has its own real part and imaginary part. So in the convention of the textbook, you use a real part as u, and then the imaginary part is v. Okay, and obviously f depends on z, so u can depend on z, and v can depend on z also. But when we write it like a u and v, both are real. These are real function. V are real function. Then we can actually write out express the dependency on the real part and imaginary part of z instead of just z. It's x and y. The u and v's are a function of two variables, x and y. So for any given function to decomposing in this form is straightforward. Sometimes maybe take some work, but then most of the time it's not too difficult. You can, in general, write a function into this form. Okay, so that's the convention how you express this complex function. Now the next idea is we can define the derivative of a complex function, right? And we can define a derivative of a function, say df dt, just like a derivative of a real function. Now we try to define a derivative of a complex function. All right, and the idea would be fairly straightforward. It's just like the same definition as a real function. Is the limit of the increment of z tends to 0, and that is z minus fz divided by z. Okay, so that's I mean, if you change z to x, it's just exactly the same as if you define the derivative of a real function. The complication is that z is a complex number, so it's represented in a complex plane. So, like, consider this point as a z. This is your z here, right? And this derivative involves z plus delta z, the function at z plus delta z, but then it's in a two-dimensional plane, so delta z can have a direction. So if this point is your z plus delta z, so this difference is your delta z, right? But then it can be can point in any direction. If this delta z can approach 0 from different direction. Okay, so if this limit depends on how you change delta z to see how you approach delta z approach 0 from different direction, then obviously this object does not exist. So the FDD will not be well defined if this limit depends on the angle approach, because this just specifies delta z going 0. You can go in 0 from different direction. Okay, so whether this derivative exists or what we call the function is differentiable depends on the property that this limit is independent of how you approach 0, what direction you approach 0. Okay, so that's the idea. So so first we define differentiable. So if a function derivative this object exists, then they require that this limit is independent of the direction of how delta z goes to 0. Okay, so that's the first concept. And this concept is powerful because now immediately you can derive a condition which is very useful, what we call the Cauchy-Riemann condition, out of this consideration. So if you assume this exists and this process is independent of delta z, then we can take the delta z approach to zero using two directions, right? And like if delta z, because delta z is x per I y, right? So delta z will be delta x plus I delta y. Right? Now you can choose, you have two choices. You can first set delta x to zero or delta y to zero. So you have at least two directions. One direction is delta, like if delta y is zero, you approach zero. This delta z approaches in the direction of this real z axis. And the other way, you set delta x to zero, just changing delta y is approaching zero along the vertical or the imaginary axis. So you can do the same thing um, using these two directions, and then if this exists, then the two should be the same. That's okay. So we'll try to derive this Cauchy-Riemann condition this way. So first, you can, like if you choose delta y to zero, that df dv, just like what we hear. Now delta y is zero, so delta x is zero. Okay, and you have this now as f z is the z, and delta z is now just delta x, right? And one is now divided by delta z is just delta x, right? That's so far so good. Look forward to do this. Sure. Right, and now you go back to this expression, write it in real part, imaginary part of f. So this, we have two parts, u and z. So you have u, but both of these two terms both have the u and v. So we write one at a time. So for the first one, so x change to x plus delta x, and y, because delta y is the same, so y is the same, and then plus I. So we do the same as for v, is delta x, and then y. Okay, and that's this one. And they subtract the other way, which is just u minus v x minus my delta. Okay. Now you group the terms, real and imaginary parts. The real part is this one minus this one. Imaginary part is this one minus that one, right? And then by the usual, now these are real function. U and v are real function, and delta x is also real. Now you can do the same thing, just the usual calculus, the definition of derivative. So this minus this divided by delta x, but this is subject to delta y. Right? And by the usual definition, this minus that divided by delta x, taking the limit of delta x go to zero is a partial derivative. So u x, right? And one remark about, you know partial derivative, right? You learn about derivative. But I, most likely you learn that, but this remark is for you to remember that there's a subtlety when you write this notation, because people usually are lazy. When you write positive derivative, supposedly you need to you need to indicate what else is keep fixed. In this case, y is keep fixed. So the full notation, you should have a subscript or a bracket and subscript y, indicating that what else are kept constant. In this case, y is kept constant. And but in many situations, people are just don't want to write that many things. Just ignore all this, just implicitly assuming that you know that they're keeping y constant. And in most cases, it's not it won't cause trouble. But in some cases, especially when you do change a variable, like sometimes you want to change y, so if y is another function x plus another variable, then there's an x implicitly in y also. That will cause you trouble, right? Uh, so uh, you need to be a little careful when you work with partial derivative. But for us, this is quite obvious because we are only two variables, x and y. Without partial derivative of x means that you keep y constant. Likewise, partial derivative of y, you keep x constant. Okay, so that's so that we can avoid all these subscript. Okay, so the real part is partial u partial x, and the imaginary part is likewise. This is this minus that, so this is partial v partial. Is that okay? So that's approaching zero. That is approaching zero with delta y equals zero. Okay, and now we can do the same thing for the other case. In this case, I need to erase it because there's not much space here. So we do the same thing now with delta x is zero. So let's start from here. Is that a question?
Yes. So we have that.
Yeah. This one?
That graph. Yes, the graph. So
the graph.
Yes.
Okay.
So in that case, in our case here, we are taking that for both the first and the second contract. What is the what's in terms of if we are talking the
well, this is this delta z. So this z is this point. We want to define the derivative of z at one location. I just choose this point. But this definition is the same that you evaluate the function at z plus delta z. So z plus delta z can be any point. The z plus delta z. So this point is z. This is z plus delta z. Right now it's in this direction, and then that the definition is we want delta z equals zero, which is this point will go to this point, and then take this limit, right? And then we define a dfdz this way. But then the problem is that this delta z can be this way, but it can be this way, this way. Any direction you can go through with this process, and this limit has to be the same if dfdz exists. If you take this approach to zero from different direction, you get different limit. Then this obviously this dfdz does not exist. It's not well defined. So we say the function is not defensible. Okay. So we are now the first case. We assume it's defensible. We assume this process is independent of the direction of how delta z goes to zero, and we try to divide what we call the Cauchy Riemann condition. So, and the process is let delta z go to zero two ways. One way is delta y goes to zero. The other way is delta x goes to zero. No, we already finished the first approach that delta y is zero. You get this. dfdz equals to this one. Okay. Now we go to the second one. Set delta x to zero. Is okay? Yeah.
this only happens if, for this case, delta y is equal to 0, right?
Yeah, this is delta y is 0. That's how we define the partial derivative.
Yeah.
So this one minus this one divided by delta x is the partial derivative if we keep y the same. So y is the same here. Y is, right? That's how you define the partial derivative. All right. And we'll do the same thing now with respect to y. So we will have a partial y instead. All right. So now the next thing is EFDC. Now it's limit delta y goes to 0. Now it's u x y plus delta y, and then plus I v y plus delta y, and minus u x y minus I v x y. So this is this one. And then we divide it by delta z. Delta z, in this case, delta z with delta x is 0. Delta z is I times delta y. It's okay. Now we'll do the same thing, separate this expression in the real and imaginary part, except the complication is that there's an I in the denominator. So this minus this divided by delta y is actually imaginary part because you have an I in the denominator. And you know 1 over I is just minus I. Okay. So this minus that divided by I will give you the minus of I times this minus that divided by delta y, which is the partial u partial y. But that is in the imaginary partial u partial. That's in the imaginary part. Now for the v, this minus that, there's an I here, but there's an I in the denominator, so you cancel all the I. This cancel with that, this cancel with that. So v, this one minus that one divided by delta y. So by definition, it's partial v partial y. That's in the real part. The real part is partial v partial y. The imaginary part is partial minus partial u partial. Okay. Now we have two expressions, df dy. This one equals to this one, now equals to this one. So whenever you have a complex expression, a complex equation, so you need to, because complex number has two parts, you want to require both the real part and the imaginary part to zero individually. So the real part must be the same when this one equals to that one. And the imaginary part has to be the same. So the imaginary part of this equals the imaginary part of that. So this implies the real part is this partial u partial x. The real part in here is partial v partial y. Okay. And the imaginary part of this is partial v partial x. And the imaginary part of this is minus partial u partial y. Okay. And so these two are called the Cauchy Riemann condition.